Thanks for coming today. This is our first lecture series put on by the UBC Astronomy Club, and today we have an extremely dynamic speaker, Jaymie Matthews, and he's going to be talking about prospects for life around Proxima Centauri B. So we'll just pass it over to him. I'm sure you don't want to hear me talk anymore, and enjoy.
I have been dynamic. I'm actually working on this talk all night and right up until I left for UBC, so hopefully I can stay dynamic for another hour. Warning, it might be a little longer than an hour when you do things at the last minute. You always overpack. That's the way I do when I travel. But there are places where I can cut off, and the exits are right there, so I managed to get in through that control room. That wasn't locked, so there are plenty of places to bail out. Last week I was in the Okanagan, in Vernon and Kelowna, giving public talks and guest lectures at Okanagan College and high schools. And on the Monday night I was in Vernon speaking up against the U.S. presidential debate. And so I couldn't resist sharing the thought of Trump. And to be fair, both sides. The two-party system in the States. Don't even comment on some of the things the libertarian candidates would say. But the fact that Donald Trump is urging you to trust that picture might give you pause, and we'll come back to that later. So let's start with the star. It's our nearest neighboring star. Alpha Centauri, which is actually a binary star system, so Alpha Centauri A and B is the brightest of these stars visible in the southern sky. Beta Centauri, but Proxima Centauri is that one. It doesn't really stand out. It's less than, fainter than 11th magnitude, so not visible to the naked eye, but is visible to binoculars, but still not a spectacular sight even there. Once you zero in on that part of the sky, if you didn't have that glowing neon yellow arrow to point out which one was Proxima Centauri, it would be very hard to distinguish it from the other jewels in the jewel box. First, I'd like to talk, it is our nearest neighboring star beyond the Sun. So how close is Proxima Centauri? And rather than saying, well, it's 4.2 light years, I wanted to give it more perspective. Now here's a map of the sky, which includes Alpha and Beta and Proxima Centauri and the Southern Cross and so on, which is a good sky navigation aid. And what I want to do is actually make not a star map, but a map, and make it a road map to kind of guide us to the next stellar destination in our neighborhood in the galaxy. And so this is going to be something, it's a thought experiment. It's what Einstein would call a Gedanke, where you do something which is impractical to do in reality, at least under the circumstances, but you can imagine doing it and you can deduce something of the results from that thought experiment. And so the thought experiment here we are floating in this giant chestnut in the nest or the new sub overhead. We're going to lay a big piece of paper on the floor. We're going to clear out all the chairs that you carefully laid out. And we have to decide on a scale on the map. And in some sense, where you've sat, or some of you have sat, we'll decide on the scale, because I'm going to ask for 2 volunteers. And don't worry, you don't actually have to do anything. That's the best kind of volunteering. I'm sure that's the kind of volunteering that Donald Trump has done in the past. So let's see, in terms of separation, what's your name? Teresa. Teresa is going to be the sun on our map. And so on our imaginary piece of paper where she is sitting, she would take a pen and mark a dot, and that would be the sun. And roughly a meter away from Teresa is Agnetha. She's going to be the Earth. And she is going to mark a little dot on the piece of paper there. And that is going to establish the scale of our map. You always have to have a scale. And in this case, every meter will represent the average distance between the Earth and the Sun. What astronomers, as you probably well know, call the astronomical unit, or the AU. which is about 150 million kilometers. So now all we need to do is figure out where we're going to put the dot that represents Proxima Centauri, our nearest neighboring star beyond the Sun. So let's give it a location here. Here's a map of Metro Vancouver showing where we're located in the UBC campus in Point Grey in the nest. We zero in on some more detail. We're at level 2 of the nest in this performance theater, and I had never realized what it was called until today. And there's the view for the poor peons who aren't part of the Circle of Trust experiencing this here. And I couldn't find a floor plan for this, and I realized why. Is because there are no permanent seats or anything, so it's a fairly simple thing. Here it is. So I just sort of improvised a floor plan at the last minute for the nest. And I didn't instruct you to lay out the chairs the way I put them here, but hey, what are you going to do? So now, and I have 2 people sitting about a meter apart, not quite in the same seats as I have here, but that's our scale, 1 meter apart, Earth and Sun, and that means every meter on our piece of paper represents 150 million kilometers. So then, where do we put Proxima Centauri? Well, it turns out we need a bigger piece of paper, a bigger map. So here's a map of Metro Vancouver again. We still need a bigger map. Map of British Columbia. Now we're talking. And here, the scale on this particular map, that arrow represents 300 kilometers in distance. 300 kilometers happens to be roughly the distance straight line distance from Vancouver to Kelowna, which is where I was last week speaking during Science Literacy Week. And that's where I was last week, and on our map, that's where Proxima Centauri would be, actually on the other side of Kelowna. And so that's the size of the piece of paper we need for a map, just to put our nearest neighboring star beyond the solar system on that piece of paper. And I remind you again, every meter on that piece of paper translates into 150 million kilometers in an outer space. So 4.2 light years is the closest stellar neighbor to the solar system, but on human terms, it's an incredibly large distance. And if you want to travel there, and the Russian oligarch behind the Breakthrough initiatives is funding something called Breakthrough Starshot, where there will be nanosatellites, tiny satellites, or at least the plan would be for these fleet of very tiny satellites to be propelled towards Proxima Centauri by the pressure of laser light, radiation pressure of laser light on large sails. It's called Breakthrough Starshot. And maybe if all of this is possible, and there are lots of technological hurdles yet to overcome, in principle, one could send this fleet of tiny probes to Proxima Centauri in about 20 years. It would take 20 years to get there. But the fastest trip, of course, would be at the speed of light. But that's a pretty strict speed limit. And so at a speed limit of just over 1 billion kilometers per hour, it takes over 4 years to get to the next star. Just to put things to scale, so the question isn't really how close is Proxima Centauri, it's how far it is, how far everything is. So here is a set of distances for our solar neighborhood on a logarithmic scale, so we can squeeze in a lot of things. So as you work your way rightward, every tick mark represents 10 times larger distance than the tick mark to the left of it. And we define the boundary of the solar system as the heliopause, the kind of the shock wave for the sun's magnetic field and the cosmic rays, charged particles coming from the rest of the galaxy. A much larger analog to the Earth's magnetopause interacting with the solar wind. And the Voyager 1 space probe has actually crossed that. So technically it has left the solar system, but it has a long way to go to get into proper interstellar space. And at the rate that it's traveling, even at the rate that the fastest space probe that we've shot out from the Earth, the New Horizons probe that passed Pluto and Charon, and it's the smaller moons of the Pluto system last summer, it would take tens of thousands of years to reach the distance of the nearest star. So again, the answer is really how far is Proxima Centauri? 4.2 light years is close by astronomical standards, but very distant by human standards. By the way, if you did get to Proxima Centauri and looked behind you at night, you would be able to see our sun in the sky, and you could make a map of the skies from Proxima Centauri, and our sun would be part of a constellation in the skies of Proxima, and this is what that constellation would look like. So, got the distance of Proxima Centauri. What about the size of Proxima Centauri? Well, again, it's not how big it is, it's how small it is. So here it is shown compared to the Sun, and Alpha Centauri A and B, which are solar analogs, comparable in size to our own Sun. Proxima Centauri is a red dwarf star, or an M-type dwarf, one of the coolest in our stellar classification scheme. And it's even relatively small compared to giant planets. Here it is shown to scale with Jupiter and Saturn. Jupiter and Saturn are composed mostly of hydrogen and helium. Their composition is more similar to the Sun than it is to the Earth. And you might wonder, although Proxima Centauri is substantially more massive than Jupiter, the mass-diameter, mass-radius relationship for gas giants and brown dwarf stars and low-mass M-dwarf stars is not a simple linear relationship. And in fact, Jupiter is close to the largest that you could get for a gas giant planet, even if you dumped tremendously more mass on it. And so it's a little bit counterintuitive. So here are the properties of Proxima Centauri. Spectral type, I said it's an M dwarf, that M5.5, Roman numeral 5, that's what the V is, tells us that it's a main sequence star, it's in its stable adult life, and it's quite cool. It's cool for a number of reasons, but I mean cool in temperature. Its mass is only 12% of the mass of the Sun, its radius only 14% that of the Sun, and its luminosity, 1.6% of the Sun's luminosity, so it's tiny and dim. And should be putting out a lot of light in the red and infrared because its temperature at the surface is about 3,000 Kelvin, or about 2,700 degrees Celsius. Rotational period, it's actually rotating quite slowly, which should mean that it's a kind of a boring, fairly settled star. It's older than the Sun by a bit. The Sun and the solar system about 4.5 billion years old, and Proxima Centauri about 4.9 billion years old. And the Sun has settled down into kind of a very dull middle age, which is good for us, because it doesn't do exciting things like explode. And so we'd expect that for Proxima Centauri, but we don't always find what we expect. Metallicity, that's astro speak for the composition, the concentration of heavy elements, in this case scaled to the concentration by mass of iron compared to hydrogen, and that 0.21 dex on a logarithmic scale tells you that Proxima Centauri is richer in heavy elements than the Sun. An astronomer would say it's a metal-rich star, which is kind of good news in terms of the heavy elements are the building blocks you need to make terrestrial planets and to make life, and so we know that at least the star has come equipped with those, and so the raw materials from the nebula that went into making the star also should have been equipped with those raw materials. As I said, it's relatively faint in our skies, about 11th magnitude, 4.22 light years away. So I'm going to be telling you about what is putatively an Earth-like planet in a very general sense around the star Proxima Centauri. And I'm going to tell you how it was discovered, but it wasn't discovered in a photograph, in a CCD image. We have very large telescopes, we have very sensitive CCD detectors, and yet that's not the way that we discover most planets. And in fact, it's not the way that we could discover even a planet around our nearest neighboring star. So I want you to think about what it would be like to take a picture of an Earth-like planet orbiting a red dwarf star like Proxima Centauri, which is about 4.2 light years away. So it's just this pinpoint of light in our sky. And the analog to that would be to taking a photo of a grain of sand on a person's finger. And so basically, I don't even want to see it, I don't need to resolve it, I just want to measure the light reflected off of that grain of sand. So we're seeing the person by reflected, say outdoors, by reflected sunlight. We're seeing the grain of sand by reflected sunlight. We'll zoom in, there's the grain of sand, 0.3 millimeters across is what I assume for the calculation. And so taking a picture and detecting the light scattered back to us by an Earth-sized planet around Proxima Centauri, 4.2 light years away, is equivalent to measuring the light that's reflected back to us by a grain of sand on a person's finger when that person and the grain of sand are 1,000 kilometers away. So that, and you can't even, I haven't even bothered to put a little thing there because you just wouldn't be able to see it. Fortunately, most people. In the infrared we glow, just like planets glow brightly, and if I have time I'm going to talk a little bit about that. But at visible wavelengths, what you and I see by eye, then the light would just be too faint. So here's that image of the sky with Proxima Centauri roughly centered in it, otherwise you'd have a hard time spotting it. So how do we know that there's a planet which we've dubbed Proxima B? The formal name would be Proxima Centauri B, but Proxima B kind of rolls off the tongue nicely. Well, we use physics, and we use a technique that was actually pioneered right here at UBC and at UVic by my friends and colleagues. One now retired, the other had left astronomy to go into consulting and business. Gordon Walker here at UBC, and Bruce Campbell, not the Bruce Campbell of Army of Darkness and Evil Dead fame, but the Bruce Campbell of Discovering Planets fame at UVic. And the point is that if a planet is orbiting around a star, the star is not nailed down in space. It has to move in reflex to the orbital motions of the planet, because the reason the planet is orbiting is due to gravity, and gravity is a two-way street. It's a mutual attraction. But because F equals ma, force equals mass times acceleration, the mass of a star like the Sun, for example, is more than 300,000 times the mass of the Earth. And so therefore, while the Earth is accelerated in a large orbit, one astronomical unit, 150 million kilometers in approximate radius, the orbit of the Earth is close to a circle, then the Sun is also forced to move, but the acceleration is 1/300,000th out of the Earth. But it's not zero. And even though you can't see the planet, if you can measure the wobble of the star, then you can detect the planet. And because the wobble of the star will have the same period above this balance point center of mass as the unseen planet. Now, looking down on this planetary system, if you can measure the change in position of the star in the sky, that would show you there was a planet there. But we don't have the angular precision yet in the technique called astrometry to do that. However, if you're looking at the orbit at an angle, and I'm showing it at the most extreme angle, edge on, but it doesn't have to be edge on. The planet doesn't have to pass directly in front of the star. Then the star will move towards us and away from us in a periodic pattern. And we can basically look at the light emitted by the star and measure the features in its spectrum, the absorption lines, and see how the wavelengths are shifted back and forth by the Doppler effect. Now, this is the advance that was made by Gordon Walker and Bruce Campbell at the time in the late 70s when they started their technique. The most precise measurements of the velocities of stars were about 1 kilometer per second, 1,000 meters per second. But you needed precision that was measured in like tens of meters per second or less in order to detect the wobbles of stars due to planets. And they developed a way to improve the precision of stellar speedometers by basically 2 orders of magnitude. And I'm going to show you some results today where the measurement precision is down to approximately 1 meter per second or less. So what you do is you measure those over time, and then you see that the star is wobbling back and forth due to an unseen dance partner, and you plot up what we call a radial velocity curve or an RV curve. And this curve is actually for one of the earliest exoplanets discovered outside the solar system. And you can see the period of the planet by the period of that sine wave. The fact that it looks like a sine wave tells me that the orbit of the planet is nearly circular, and the amplitude of that radial velocity curve gives me a lower limit on the mass of the planet. It doesn't tell me the mass of the planet because I don't know how the orbit is tilted. And depending on how it's tilted, then the mass of the companion, if it's a steeper angle, will be higher. And so all I know is the minimum mass if the orbit were almost in the line of sight. Here is one of today's best speedometers for stars. It's HARPS that you see in the lower left there that's attached and receives light from this 3.6 meter telescope in La Silla in Chile, and they enter the Atacama Desert, arguably the driest place on Earth. Parts of the Atacama that haven't seen measurable rainfall in recorded history. ESO here stands for the European Southern Observatory. And HARPS stands for High Accuracy Radial Velocity Planet Searcher. To be honest, the semantics, it should be High Precision, but then that wouldn't have been a very pronounceable acronym. So I'm going to cut them some slack there. And in fact, it was this telescope and this instrument which played the key role, the pivotal role in the discovery of the planet Proxima B. And so here is, at night, that 3.6 meter dome. The one beside it, by the way, is a kind of a Coude auxiliary telescope, and you can bring the light from either of those telescope domes to the focus of the same instrument. And there's Proxima Centauri labeled, and some of the other stars that I've already talked about. And here are some of the radial velocity data from 2 months earlier in this year, in which you see a simple sine wave fit. There's scatter in the data, but I think you could convince yourself that there is something which is going up and down roughly periodically. Guillaume Anglade-Escude and partners published this in Nature in August, and I was part of the behind-the-scenes work in this for a few months before it became publicly known. Here is what we call a phase diagram of the data, including additional data and data from another instrument from another European Southern Observatory telescope in Chile called UVES, ultraviolet, I'm blanking on the E for spectrograph, Echelle, ultraviolet Echelle spectrograph. And so what we've done is basically at a trial period, if you think you can identify and you don't just do it by eye, you can do frequency analysis, Fourier analysis, and so on, and you find the likely trial period, then you just fold the data over on each other at that trial period, and if you get something that looks like a coherent curve, then you're on the right track. But see, we're at the kind of limit of the detection here, because Earth mass, the smaller the mass of the planet, the lower the amplitude of the signal. So this is an 11.2 day period. The peak-to-peak amplitude of this variation is only 2 meters per second. And you can see the error bars and the scatter and the various data sets. So it's just, at the level of detection. So I told you the properties of the star, Proxima Centauri. Here are start with some of the properties of the planets. Proxima B. And we don't know that much about Proxima B. That's just the name of the game when it comes to exoplanets. And in this particular case, I'll tell you why we don't know more than we would otherwise like. The planet type there, this is something that people at the Planetary Habitability Laboratory in Spain have come up with these categories, and so they classify it an M because of its temperature type, M-type star, warm Terran because it's a relatively small planet with a solid surface. Mass, again, because we only have the radial velocity data at this moment that I've shown you, the mass is a lower limit of about 1.3 times the mass of the Earth, with an uncertainty of about 2/10 of an Earth mass. The radius we can only infer, assuming that it's made up of a primarily rocky composition. That would put it at least about 1.1 Earth radii. Period, as I said, about 11.2 days. That's its year. It goes around the star once every 11.186 Earth days. Sunny major axis, that's the average distance between the star and the planet. That's how we would characterize the size of an elliptical orbit, 0.05 AU, just from the units, 1/20th of the size of the Earth's orbit, smaller than the orbit of Mercury, and I'll show you a comparison in a few minutes. Eccentricity is how elliptical is the orbit, and because of the scatter that you can see in the noise, it's hard. You can fit that with a sinusoid, but you could also fit it with some other non-sinusoidal curves, and so all that we can do is put an upper limit on the eccentricity of 0.35, which is pretty large. Mercury has the largest eccentricity of the planets, now that Pluto has been downsized to the status of a dwarf planet. Its eccentricity is 0.2, so this is fairly eccentric. So let me just show you then the orbit, given these categories, or orbits. There is only one orbit, but in terms of possible orbits, here are the two extremes. The one shown with the maximum eccentricity value, the most elongated orbit that it might have, and the minimum eccentricity value, which would be a circular orbit, where the eccentricity is 0. And you notice how it's going in and out of that green zone. And that green zone is something called the habitable zone that I'm going to talk about. And so if it is in a very eccentric orbit, then that might have implications for, it will have implications for the habitability and how life, whether life would be able to get a foothold on it and evolve in the star. But almost everything you've seen in the media and even in a lot of the science reports tend to emphasize eccentricity equals 0, and they kind of downplay the E equals 0.35, because that's a little less favorable for it to be habitable. Planet itself, the mass, as I said, is a minimum value. Now, if we want to try to at least infer its size, again, it's not how big Proxima B is, but how small, it's comparable in size to the Earth. And that's assuming that minimum mass value from the RV data and assuming that it has a rocky composition similar to the Earth. And those are assumptions, not known facts. So the fact is we don't actually know the planet's diameter. And so it's possible that it may not be as Earth-like as the minimum mass suggests, but there is a high likelihood that it does have a kind of metallic rocky composition that would be like Earth. How could we figure out the diameter? That's through another technique for detecting and characterizing exoplanets beyond the solar system, transits. If you're lucky enough that the orbit of the planet is almost in your line of sight, so that the planet actually passes in front of the star during its orbit, then when it does, it chops out a little bit of the disk of the star, and it causes the starlight to drop slightly. The larger the planet, the bigger the drop. The drop lasts for like 2.5 hours, and it repeats again and again as the planet passes in front of the star in its orbital period. And this is the only way, actually, that we can measure the diameter, the radius of a planet around another star outside of our solar system. And so transits are very important, but even if all stars have planets, and if those planets' orbital planes Space Telescope, using Canada's Space Telescope, called MOST, shown here side by side to scale. MOST was designed, built, tested, and is still operated under my supervision here at UBC, with a station in Vienna and an aerospace company operations in Mississauga outside of Toronto. MOST stands for Microvariability and Oscillations of Stars, Microvariabilité, Oscillations Stellaire, which is what it was designed to study, and transits and planets turned out to be in the category of microvariability. Because, although that's the official name, because of this comparison with the Hubble Space Telescope, not only in size but in budget, we nicknamed it the Humble Space Telescope. And after it was launched, people recognized that we had stolen elements of the design from a famous Hollywood celebrity, so I sometimes feel legally obligated to call it Space Telescope SquarePants. SpongeBob has become a mascot. Most SpongeBob doesn't take pictures in the conventional sense, nor does it obtain spectra. It's a light meter in space. It was the pioneer for missions like the NASA Kepler mission, and before the Kepler mission, the French Corot mission, which was just celebrating its legacy in Paris this weekend. I was supposed to be there, but had to cancel. Here I am in the bunny suit, my bunny suit, beside SpongeBob on his head in the clean room before launch, and with the instrument taken out. So it's about this, as you've seen, about the size mass of a suitcase. You can check it onto the plane, and Air Canada can lose it for you. And it's designed to see changes in the brightnesses of certain stars as small as 1 part in a million, 1/10,000th of a percent. Even astronomers have a hard time wrapping their heads around changes in brightness in flux as small as 1 part per million. And if astronomers have that problem, you can bet that federal bureaucrats in Ottawa that you're approaching for funding your project have that problem. So I had to come up with a way to explain this to a non-rocket scientist, and this is what I came up with. Imagine going to New York City and looking at the Empire State Building at night. All of the office lights are on, all of the office window shades are completely open. You could make the Empire State Building dimmer and reduce its light output by 1 part in a million, 1/10,000th of a percent, by having one person stand beside one window and pull down one window shade by 3 centimeters. And MOST was the first instrument capable of that sensitivity for stars. So it was the pioneer, and it is still operating. It was launched in June of 2003, day before Canada Day. It was intended to be a 1-year mission to observe 10 stars. We've now been in space for more than 13 years with about 5,000 stars under our belts. SpongeBob is the gift that keeps on giving. And so we observe Proxima Centauri to look for transits. And it's a challenging thing to do because the orbit of our satellite, it's designed to be able to stare at stars for up to 2 months at a time, but in a band of the sky which is roughly oriented by the celestial equator. And yet Proxima Centauri is nowhere near the celestial equator. In fact, it's about 40 degrees south of the lower limit, the southern limit of what we call the continuous viewing zone, or CVZ. But the science was compelling enough that we figured out a way to kind of keep moving the satellite, the telescope, to point there for part of each MOST orbit, and MOST orbits the Earth once every 101 minutes. And we did a trial in 2014 for about 12 days, and then we learned some lessons from that, and we were able to cover it for more than 3 weeks the next year. The peaks there that you see, the big sharp spikes that look like delta functions, those are strong flares, and I'm going to talk about those more a little bit later. But if you're looking for planets, you want to get rid of the flares at least that you can identify, and we haven't gotten rid of all of the flares. The reason these light curves look so noisy is because Proxima Centauri is a noisy place. That's not instrumental noise, that's in the star itself. But there are the light curves now, and then rescaled, of course, because once we've taken out those big peaks, now you can see smaller level variations. And we did the same trick that I showed you for the radial velocity data. We folded them at the period of the planet Proxima B that was detected from the Doppler wobble. And here is that phase diagram showing some evidence for a transit. The two panels, the folded original and folded alternative, I won't go into the details. We did a lot of statistical analysis. And ultimately, you never want to be, the old story, the boy who cried wolf. You never want to be the boy who cried earth. You don't want to claim something and then have to retract it. And so our decision, the team, and my partners in this are David Kipping, who started out at Harvard, who began this now at Columbia University, James Davenport, and others. We decided that the title of our paper was No Conclusive Evidence for Transits of Proxima B in Most Data. But to be honest, by most standards, this would qualify. And a number of planets which have been reported by the transit technique have even less evidence for that. So we want to just follow it up and corroborate it, and rather than just claiming early glory and then finding out we're wrong, we're happy to be slightly humble, but hope that we can verify that this is that, because then it would tell us the size of the planet and the density of the planet, and we can certainly use these data to infer that, at least as kind of a trial. On the list of properties, we can also figure out how much flux, how much energy per second per square meter falls on the surface of Proxima B, or falls at least at the top of the atmosphere, if it has an atmosphere. And that would be 70% of what we receive from the sun here on Earth. So in my title slide, I showed you this artist's conception of Proxima B with the star Proxima Centauri, which is officially now Proxima Centauri A, because it has that companion. And Donald Trump has asked you to place your trust in him, that this was a realistic picture. That should raise some alarms. PolitiFact keeps track and verifies his statements, and he won the Political Liar of the Year award in 2015 from PolitiFact, and here are the 2015 the things where he owned the podium. Notice that there is only one political statement that he made in 2015 that could actually be verified as true, and what is that? 18 that qualify as pants on fire, which are just so outrageously untrue that there's no other way to describe them. Now, is that painting I'm showing you? It's not a pants on fire. It's not even really false. Mostly false. It kind of falls in the mostly true to half true category. The angular diameter of the star as seen from Proxima B is represented well here, although you might not have enough information to recognize that. From the surface of Proxima B, its sun would look about 3 times the diameter in the sky as our sun looks in ours. It's a much smaller star, but Proxima B orbits much closer to it than we do to our sun. Proxima B likely has a solid surface. I realize I screwed up some slides here. I'll try to repair that later. I told you I was working right up into the last minute of this. It does likely have a solid surface. We don't know its radius, but and we only have a minimum mass, but I think this is a fair bet that it is a solid rocky planet. And in this shot, Alpha Centauri A plus B are actually photobombing the painting in the background sky. And they would be very bright stars in the skies of Proxima B. And the star is shown looking red, and it is true that Proxima Centauri emits more red light than the sun. But it wouldn't look so dim and red in the skies of Proxima B. It would look more like this. And the reason is, well, if we look at the flux, it's receiving about 70% of the flux that the Earth receives from the sun. And so I want to just make a little detour on the basic physics of light, how brightness and temperature and color are related. And here's an incandescent light bulb. These things, I think, are illegal now in British Columbia, but and if you take away the frosted glass and so on. There's a filament, you run a current through it, that heats up the filament, that's what causes it to glow. And when it's cooler, it's dimmer and redder. When it's hotter, it's brighter and whiter. Here's another example of the same phenomenon, the sun. And they're both examples of what a physicist would call a black body. Maybe counterintuitive that you're talking about something very bright as a black body, but it's not the only silly thing that we do in physics and astronomy. So the definition of a black body is basically any object which is emitting radiation due to its surface heat, and you're not seeing it by reflected light. So yeah, if you switch off the light bulb and you're looking, you can see the filament of the unfrosted glass, you're seeing it by reflected light. But as soon as you switch on the current, then all the light you're seeing is from the glow of the filament. Same for the sun. The sun is reflecting light, scattering light from other stars and from the planets, but that's negligible compared to its own emission. And a black body emits radiation in a specific way as a function of wavelength. And so here I'm showing this. Any body that's warm, and what I mean by warm is warmer than absolute zero, warmer than 0 Kelvin, warmer than minus 273.15 degrees Celsius, its intensity varies with wavelength in a way that depends only on its temperature, not on its composition, not on its shape. And what I'm showing here is flux, essentially the emitted energy that's escaping from the square meter of the surface of this body every second. And so it's, if you, at any given wavelength, you're talking about the energy of a single photon multiplied by the number of photons leaving the surface per second divided by the area of the surface. And in terms of energy, energy goes inversely as the wavelength and linearly with the frequency. And so this plot of flux, energy per area per time, is known as a black body curve. The physicist Max Planck actually figured out why things behave that way. And so he derived the physical mathematical expression for that curve, and so we also call it the Planck function. So this particular black body source is putting out most of its light in the part of the spectrum that you and I see by eye. And it turns out it has a temperature about 5,000 Kelvin. It's only a little bit cooler than the surface of our own sun, which puts out most of its light at wavelengths that we see by eye. Maybe not a coincidence that we developed on a planet orbiting the sun, and our vision is reasonably well matched to where that sun is brightest. However, a cooler source puts out less light in total. This 4,000 Kelvin source, which is now getting into Proxima Centauri territory, puts out less light in total, and its peak occurs at a longer wavelength. And a hotter source, this would be like a hotter star, this would be in the realm of an F-type or an A-type star in our astronomical temperature scale, puts out more light in total, and its peak emission occurs at a shorter wavelength. That dependence on temperature and the peak emission wavelength is known as Wien's law, named after an Austrian physicist, and where basically the wavelength in which the source is brightest is inversely proportional to the temperature. And we see examples of that in our everyday life. If you are heating up something in a fire until the coals are glowing cherry red, they're just reaching the temperature where there's enough light coming out of the visible part of the spectrum that we can see it. And an arc welder's torch, the reason that you wear the helmet and the visor isn't just to protect yourself from sparks, but is because that's at a temperature, that arc is at a temperature where a lot of the radiation is coming out at ultraviolet wavelengths, which could be permanently damaging to your eye. The other thing, I said that things put out more or less light in total depending on the temperature, and the total flux would be the area integrated underneath the Planck spectrum, the black body curve. That goes up as a function of temperature as well, and only as a function of temperature, but much more dramatically than in Wien's law. It's a temperature to the 4th power. This is the Stefan-Boltzmann law, And so if you double the temperature, basically you increase the total flux emitted from the surface of the black body by a factor of 16 times. And so now in this diagram you actually see something which is more relevant. Here is the temperature of Proxima Centauri, A, the star, and here is the temperature roughly of the sun. And so you can see that Proxima Centauri is putting out less light per square meter per second, but it's putting out in the visible most of its light in the red, and the sun would be putting out more light in the sort of yellow-green. So stars have different colors because of Wien's law, because they behave as black bodies. And here is a long exposure image of Orion. And some of you may have obtained images like this yourself at the UBC Astronomy Club Star Party or elsewhere. And the red star Betelgeuse in the shoulder, in the armpit of Orion the Hunter. The name Betelgeuse is actually a mistranslation of the ancient Arabic, which literally meant armpit of the hairy giant. And Rigel, in the tunic of Orion, the Rigel looks blue-white because the gas is actually hotter at the surface compared to Betelgeuse. But that's not what you see when you go out at night, on a clear night. Most of the stars look white. A few have kind of gentle colors, a little bit orangey, yellow, a little green here and there. Why is that? It's because the human eye isn't a spectrograph installed in our heads. And yet, physics and astronomy teachers, and even I for many years, would teach things kind of talking about the colors of stars as if we all had spectrographs built into our heads. And so that's why certain stars are red and other stars are blue. But in fact, the detectors we have built in to our eyes and the retina are sets of light-sensitive cells. Rods, which give us the black and white vision and are more sensitive to light, have a higher quantum efficiency, and 3 colored cones, each one which has a different wavelength range, and that's what gives us our color vision. And there's a close-up, by the way, of the cones compared to the rods, and you can already see in this case, you can intuitively see why the rods would be more efficient at collecting and registering light than the cones. And there are the 3 wavelength ranges. What's happening is there's basically a chemical reaction where the energy of photons is breaking up a complex organic molecule, and then it recombines later. That's responsible, by the way, for loss of night vision. That if you're out in the dark at a star party, and you've got good dark adaptation, and somebody shines a flashlight in your eye, suddenly you have a hard time seeing, and it takes a while for the rhodopsin to regenerate in the rods. And you can see there that the wavelength ranges for the 3 cones are not completely independent of one another, they overlap largely. The cones are far less sensitive than the rods. So when the light levels are low, we only see black and white essentially. That's why you have a hard time figuring out like the color of somebody's clothing if you're looking at very dim light. And the fluxes for most stars are just too low to trigger the cones. And so even though they do have colors, you've got to either collect the light with a telescope and bring it to a focus to your eye so that you can distinguish those colors, or you would have to travel in a spaceship closer to those stars to reach a point in which they would suddenly look to the colors to the unaided eye. However, if you got too close to them, you lose the color again, which is the reason why the sun doesn't look yellow-green, which is essentially its clinical, technical color. It's because the sun is so bright in our sky that it saturates all 3 color-sensitive cones, and we just see white light. So, on Proxima B, you get 70% of the sunlight. Yes, the spectrum is skewed to the red and the infrared, but there's still enough light coming through in the visible range that it really wouldn't look like some kind of dim red star. It would look, bright white with a kind of a reddish tinge to it. And this is the kind of flaw that you see in a lot of astronomical artwork and in movies and in TV shows. Usually red giants. You see red giants a lot more in those things, and they kind of glow like something that's in the barbecue as the charcoal is cooling. However, this kind of comparison between sunset on Earth and Proxima B might be okay, assuming again that Proxima B has an atmosphere and clouds which scatter light like the Earth's atmosphere does, and scatters blue light more than red. And now there's so much light that's being reduced from the sun through a much longer path through the atmosphere when the sun is on the horizon that you start to see kind of an orangey color. Now it still doesn't reflect the true black body peak of the sun, it just reflects the scattering properties of the Earth's atmosphere. And that would be true for Proxima B as well. But if it has a substantially different atmospheric composition and cloud nature of clouds, then the scattering properties would be different, and not sure. It's like on Mars, sunsets tend to look blue as opposed to red. So that's the flux arriving at Earth, and we can use that to on the surface of Proxima B. We can use that to establish the equilibrium temperature. What is the balance as the surface absorbs some light from its star, emits some of it in the infrared, and so on. The temperature equilibrium, if the albedo, which is our term for the reflectivity of the surface, is 30%. So if it actually absorbs 70% of the light it receives from the star, it would be 227 Kelvin, which is like 46 degrees below zero. So why all the excitement about Proxima B? Well, you have to remember equilibrium temperature. Thermal equilibrium assumes no atmosphere, no greenhouse effect. And if the Earth did not have a greenhouse effect is generally a nasty, a dirty word. It's a curse, for us. But in fact, the dominant greenhouse gas in our atmosphere is not carbon dioxide; it's water vapor. And if it weren't for the greenhouse effect due to water vapor, the average temperature on the surface of the Earth would be about minus 25 Celsius. So it's the greenhouse effect, the insulating effects of an atmosphere, which can make a planet habitable. And it turns out that equilibrium temperature is in the range for any variety of atmospheres and greenhouse effects to allow a temperature that makes us think about life on the Proxima B. Now, lots of people, if they were thinking about life on any planet outside the Earth, might think of it as a science fiction movie. Others might think of it as a fairy tale. And the way that we identify the first characteristics of a planet that might be able to support life is actually kind of like a fairy tale. It has elements of the story of Goldilocks and the Three Bears. But my version is Jaymie and the Three Planets. And to tell this fairy tale, I've got to come back closer to home, into our solar system. But my first stop won't be the Earth, but the Earth's sister world, Venus. Almost the same diameter, almost the same mass, thick atmosphere. For a long time it was believed that beneath the clouds of Venus, masked from our vision, was life. We now know, however, that despite the romantic name after the goddess of Venus, that Venus is a hellish place, active volcanoes, sulfuric acid, rain. It evaporates before it hits the surface, but if you're in the atmosphere, you're literally in an acid bath. And the temperature, 500 degrees Celsius. That's higher than the melting point of lead. If you went to Venus with a lead, pot, it would melt. I don't know why you'd go to Venus with a lead pot, but that's what would happen. So for liquid water oceans and life as we understand it, Venus is just too hot. What about Mars? A lot of interest in the possibility of life, at least simple life, microbes and bacteria on Mars. And Mars does have an atmosphere, and it does have water, and it does have a lot of things that remind us of the Earth, but it has them in small quantities or in not the best state for us. The atmosphere is very thin. At the surface of Mars, the air pressure is about 0.6% of what we're breathing right now. The air pressure at the summit of Mount Everest is higher than what we breathe at the surface of Mars, and it's mostly carbon dioxide. There's lots of water, but most of it is frozen in polar caps and in kind of a version of permafrost in the soil. And the average temperature, 60 degrees below zero. On a hot, balmy summer day in the tropics of Mars, the mercury can shoot up to minus 15. So maybe microbes and bacteria can survive these extreme conditions. We know of simple life that can survive extreme conditions on Earth. We call them extremophiles, and that gives us hope that there might be something that is alive on Mars or has been alive on Mars in the past for which we might find fossil evidence. But for complex life, and when I say complex life, I could be talking about mushrooms. The mushroom is way more complex than a single-celled organism. You don't have liquid water oceans as a solvent and as a transport medium, and so for complex life as we know it, Mars is too cold. Nestled between Venus and Mars is the Earth. Average temperature near the surface, say about 15 degrees Celsius. How that temperature is changing with time is a topic of great concern, as you know. But we do have liquid water oceans, and we do have life. The Earth is just right for life. It's in the zone. It's in what we call the habitable zone. That's the range of distances from a star, in this case the Sun, where the temperature at the surface of a planet that is solid, rocky, metallic, would be between the boiling point and the freezing point of water, and would allow liquid water oceans and at least one of the requirements for life as we know it. We call it the Goldilocks zone, because if the planetary bowl of porridge is too close, it's too hot. If it's too far away, it's too cold, and if it's in the zone, it's just right. It's kind of like being around a campfire. If you're too close, you burn yourself. You're too far away, you freeze to death. And if you're at the right range of distances, you can survive a cold winter night. But not all stars are campfires. There are stars that are much more massive, put out much more energy, or much hotter than the Sun, that are the equivalent of raging bonfires. But the majority of the stars in our Milky Way galaxy are much smaller and dimmer than the Sun, and cooler, and those are kind of like kindling or matches, where you have to huddle close to stay warm. And the green regions here are the Goldilocks zones around stars, and the dim, cool red stars are the M dwarfs. Proxima Centauri is part of that population. For every star like the Sun, there are a dozen of these M dwarfs. And so that's the example that we're talking about for Proxima Centauri. So not all stars are like the Sun, but in this plot here showing kind of the ranges of the outer and inner boundaries of the habitable zone due to different calculations, and that's why that kind of rainbow pattern is there, as a function of stars from the mass of the Sun down to a mass of about 1/10 that of the Sun, where the habitable zone gets closer, and a few planets which have been found. I'll give you a better example of that. Ravi Koparappu, who is one of the leading scientists in terms of giving us our best estimate of the extent of the habitable zone, who's using laboratory experiments to better define the absorbing and scattering properties of greenhouse gases to apply to the calculation of the zone, because the greenhouse effect is a major factor in it. He and I talked in Vienna last February, and we kind of regret the habitable zone thing, because it gives the impression that any star that's planted in a habitable zone could support life, and that's not the case. All it means is that it could support liquid water on its surface, one of the things that we would want for life as we know it. So here are the number of small rocky planets known to be in the Goldilocks zones of their stars, where the stars are organized by this temperature type M, K, G. The Sun is a G-type star. I put Proxima B in there, even though we don't really know its radius. So the jury is still slightly out in terms of whether it has a solid surface, but it's likely to have one, and that was the whole point of this talk. So if I just said, no, Proxima B is some fluffy thing, talk over, have pizza, go home. So I promised to show you that. Now here is the orbit of Proxima B, assuming zero eccentricity, a circular orbit. compared to the orbit of Mercury in our own solar system. So you can see how tiny it is. The green is the habitable zone, is the Goldilocks zone, and your boundary of that habitable zone. So I'm going to use Proxima B as sort of the poster child for this discussion, but really what I want to talk about is, the habitability of a star like Proxima B. So what kind of stars are suitable for life? There are things that we need on the planets, but we also need certain characteristics from the star. One is that the star should shine in a stable way long enough for life to be able to develop and evolve on a planet around it. And that's what we refer to as the main sequence lifetime, when the star is fusing hydrogen into helium in its core, producing energy, and is in hydrostatic equilibrium, a balance between gravity and gas pressure. And so here is this temperature sequence of stars going from the hottest to the coolest, O, B, A, F, G, K, M. Some of you who are astronomy students know the origins of that strange alphabet soup. If anyone's curious, I'd be happy to tell you the backstory of that after the talk. The percentage of stars in the galaxy in each of those temperature classifications. And as I told you, the M stars are the most common, and as you go to more massive and hotter stars, then they become rarer and rarer. But there are several 100 billion stars in our galaxy, so even 0.001% of 100 billion is still, 100 million stars. And the lifetimes, the more massive stars, the hotter ones, they're kind of the sports cars of the universe. They're flashy, you see them at a great distance, but they're not very fuel efficient. Whereas the M stars are the Priuses, the hybrids of the galaxy, where they're kind of dull. You don't notice them at a great distance, but they go a long way in a tank of hydrogen. And so the main sequence lifetime of the hottest stars in our galaxy is like 500,000 years. And for the M dwarfs, some cases longer than 1 trillion years. And we're in a universe that's only been around for less than 14 billion years, so that's a very long lifetime. So M stars are the most common, very long-lived, so the odds would seem to be in favor of finding planets around them and life having a chance to develop around them, and the K stars as well. But of course, their habitable zones hug close to the stars and are very thin. So here's the comparison for an F-type star, which is a bit hotter than the Sun, a G-type star, which is like the Sun, and an M-type star like Proxima Centauri. And so you're restricted to a smaller range of orbital parameters around an M-type star to be in the Goldilocks zone. So can an M dwarf like Proxima Centauri shine on life on a planet around it? And in the early going, things were pessimistic. Even when we were launching satellites like MOST and Kepler, we really didn't think that M dwarfs would be very favorable. The early work in the 60s and into the 90s said that a planet in the habitable zone of an M dwarf would be so close to the star that it would be tidally locked to its parent star, and its atmosphere would freeze on the planet's far side. It's the same effect that we have, for the Earth and the Moon. The Moon keeps the same face to us because it's been tidally locked into a ballet where it spins on its axis at about the same time that it takes to revolve around the Earth. Mercury was, until the 1960s, believed to be locked in the same way to the Sun, but we now know that it actually spins 3 times for every 2 orbits. So it is in a tidal resonance, but it's not a 1-to-1 coupling, it's a 3-to-2 spin-orbit coupling. And so it's possible that some of these planets around M dwarfs would also be locked into that kind of resonance, so there would be this kind of slow rotisserie effect. But even if that's not the case, even if it is always keeping one face to the star, more recent work suggests that you'd still get enough CO2 in the atmosphere and a greenhouse effect to prevent the atmosphere from freezing. And a colleague of mine at the University of Chicago, Pierre Lambert, modeled the environment of a tidally locked super-Earth. Super-Earth is a planet which is a bit larger and more massive than the Earth. We don't have any analogs in our solar system for that kind of planet, but we've discovered them in other planetary systems. And one of his models generated something which we call the eyeball Earth state. Planet's mostly frozen, but it has a liquid water ocean at the point of the planet directly facing the star. And here's kind of a map, square Mercator projection map, showing for an atmosphere with about 20% carbon dioxide mixed with nitrogen and with a net surface pressure of 105 pascals, what's happening in terms of where you'd have water and ice and what the surface temperature like. And this is what it would look like from space, and that's why we call it highball Earth. Even more recently, based on the discovery of Proxima B, people have used global climate models at the Planetary Habitability Laboratory to figure out what would be the range of conditions depending on different pressures of CO2 as a greenhouse gas versus the amount of surface water available on the planet. And even if it's tidally locked, it turns out that there's a fairly wide range of parameter space where you could have ice-free ocean, or ocean only partly covered with ice, or at least liquid water on the day side, another kind of eyeball Earth type scenario. And if it's not tidally locked, then you can open up things to even having lakes and a wider variety of environments that would be favorable for life, in terms at least of liquid water. But then, more bad news for M dwarfs is they tend to be very active. They have strong flares, high UV emission, even in quiescence, even when they are not particularly active. And I showed you the photometry from the MOST satellite. Here is just the first trial run, the 12.5 days, and now I've just labeled the things that poke you in the eye, the strongest flares. There were 8 strong flares in less than 2 weeks, and we saw the similar kind of behavior a year later. And here are the 2 light curves now and some blow-ups of a few of the flare events. Now, the extrapolation of our flare energy distribution, and this is a paper which we did publish in concert with the Proxima B discovery, says that Proxima Centauri would erupt with flares which would change the brightness of the star by 0.5%, about 180 times a day, like 50 times an hour. And super flares, energies of 10 to the 25th, 10 to the 26th joules, twice to 3 times in a year. And this is an Earth year, not a Proxima B year. So this has strong implications for whether Proxima B could be habitable. Because here is a 0.5%, actually less than that, about 0.1% white light flare from the sun. So, and there's the size of the Earth to scale, to give you a sense of that. That kind of thing happens, once every 2 minutes by our extrapolations on Proxima Centauri A. And we found, several in the course of a week, several 12% white light flares that would just totally blow this out of space. So that means a planet without a magnetic field would require years to rebuild its ozone layer after one of these strong flares, and they're happening very often. However, it actually turns out it might not be so bad. That even the strongest flare that's ever been observed in any star, that the ultraviolet dose that could damage DNA, is only about 19% larger than what we get here on Earth, and lasts for less than a couple of minutes. And so here are the fluxes in the UAV A, B, and C ranges, modeled for a planet around what is the most active star that we knew of, although Proxima Centauri might displace it, AB Leo. It's the bad boy of M dwarfs, at the surface and at the top of the atmosphere for a model planet. And it turns out the highest energy, the deadliest UVC radiation, is indeed higher on a planet orbiting an M dwarf after a large flare, but the fluxes are low enough as to be benign. And the UVA and B fluxes are only a little higher than at the surface of the Earth. So we may have been too pessimistic in our early assessment. Flares may not represent a significant obstacle to life on a planet around an active M dwarf star. And the thing is, although ultraviolet can disrupt cells and so on, you may need an energy source in order to trigger life in the first place. for biogenesis. And so that if you have a star which is not active enough, then that may also be bad for getting life underway. And M dwarfs versus G dwarfs, these stars like Proxima Centauri versus stars like the Sun, it turns out that once you do some, again, models of energy transfer, that in many cases an ocean-covered planet around an M dwarf would have a higher mean surface temperature than the same planet around a G star, even receiving the same fluxes of sunlight. But there is a really disturbing thing that's come to light in recent times, and we discussed this a lot in Vienna in February at a meeting on the astrophysics of planetary habitability. In the pre-main sequence phase of an M dwarf star evolution. So main sequence is the stable adult life where you're fusing hydrogen in the core and shining steadily in a balance between gravity and gas pressure. But before that, you are an embryo. And that's what we refer to as a pre-main sequence star. And when the star is still forming, planets around it may have already formed, but it turns out that the embryo for an M dwarf star is far more luminous, far brighter than the eventual star itself. And so if you find a planet which is in the habitable zone of the eventual M dwarf star, it turns out if you rewind the Blu-ray back in the movie of the system, that you'll find that early on it was exposed to much more light. The temperature would have been far above the boiling point of water, and any liquid water on the surface would have boiled away soon after the planet formed. And you can lose a lot of water, several Earth oceans worth of water in this pre-main sequence phase. And depending on what are the surface sinks, the sources to absorb that, you can actually inject up to several hundred bars of oxygen into the atmosphere of these planets. And so generally you tend to think, hey, I've got oxygen, so there's going to be life, but that's not necessarily the case. Detection of molecular oxygen in the habitable zone of an M dwarf may not indicate life. Conditions are better for stars whose masses are greater than 4/10 the mass of the Sun, shown here in the study by Luger and Barnes last year, showing position in the habitable zone versus stellar mass, and with a few pre-main sequence stars listed there. And so stars around planets above a mass of 4/10 of the solar mass, less likely to suffer this pre-main sequence desiccation, I should say, especially if they lie close to the outer edge of the main sequence habitable zone. However, remember the properties of Proxima Centauri. Sorry, it's not greater than 0.4 solar masses. It's 0.12 solar masses. Even within the uncertainties, you don't even get within spitting distance of that. But Barnes has taken a look at Proxima Centauri here, showing distance from the star versus time from 1 million years to 1 billion years on a log scale. The orbit of Mercury, the orbit of Proxima B shown here, the habitable zone as a function of time shown in blue, and then these limits, the dashed lines, are for different reflectivities, albedo. So A equals 0 means it absorbs all the light that it gets from the star, 0.5, 50%. A, that's quite reflective, that it reflects 80% of the light it receives from the star. And the blue region is actually Ravi Koparapu's most conservative habitable zone region. And so there are some possibilities that a desiccated planet, might be able to retrieve some water later in the history early on in that system. And I am doing some studies with Aaron Boley in our department, and somebody that I suggest for a future UBC Astronomy Club lecture in the series, are looking to see whether the planets may migrate, the conditions may change so that we can end up with a planet in the habitable zone of the stable M dwarf star, which doesn't boil away all of its water beforehand, liquid water beforehand. Now, I'm running overtime, and so rather than, I was going to talk a little bit about the infrared signatures of life, but I think we'll save that for a part 2 lecture. Let me just maybe end by pointing out that that's the way that we would find life. If Proxima B is able to support life, we would be looking at the infrared spectrum and looking for the signatures of oxygen, molecular oxygen, ozone, and liquid water. The three of those together are hard to have if you don't have biology. But how do you actually get those signatures in infrared spectrum? We don't have the instruments yet, but we will have some of them. I showed you America's big space telescope, the Hubble. I showed you Canada's first tiny space telescope, MOST. Here's the successor to the Hubble, roughly the same scale, the James Webb Space Telescope, JWST. And it has a light collecting mirror 6.5 meters across compared to 2.5 meters for the Hubble, so about almost 3 times the diameter, 9 times the light collecting area. The mirror will unfold like petals of a flower in space, because there is no launch vehicle in which you can fit a 6.5 meter diameter primary mirror. And Hubble's about the size of a bus. James Webb needs a bigger parking spot. It would fill up the area of a tennis court. If you don't believe me, there's the full-scale mock-up of JWST with the JWST team, part of them at least, posing at a conference. And unlike the Hubble, which looks in the optical and the infrared, or in the ultraviolet, and with a little bit into the infrared, JWST is looking almost exclusively into the infrared and far infrared. There is one instrument on it, which isn't actually an instrument, it's the fine guidance sensor for pointing it, which actually will collect data in the optical range, and that's a Canadian contribution. And we will also get science. So the only optical science from JWST will come from a Canadian instrument. And what I'm showing there are three images of a young planetary system called FOMOLO, a Hubble visible image, a Spitzer orbiting observatory infrared image, and what we expect, something like what we would expect to get from JWST. And so we'll be able to explore those early critical times when an M dwarf is forming to find out whether the situation is as bad as I've laid it out to be. And when a planet transits a star, then if it has an atmosphere, then the light from the star will be filtered through that atmosphere, and we can look for features representing, molecular oxygen, water vapor, methane, and so on in that atmosphere. And so there will be a few M dwarf stars that will likely be targets. Even with JWST, it will take hundreds of hours for a given star exposure time to build up a usable signal, so we're not going to be able to do it with many of them, probably 3. And there's a good bet that Proxima Centauri and Proxima B could be a target of James Webb Space Telescope. But there are also some other instruments that we're hoping to build in the ground in the far infrared and so on. So stay tuned for those kind of developments in the next few years. So I apologize for having run over time. I did give you a slight warning about that. But if anybody has any questions, and I know one incentive for sticking around is there is supposed to be pizza. Yeah, I see the boxes there. But depending on how eager you are to eat pizza, I'm willing to entertain a question or two while everyone's paying attention, or you can just cut to the chase and you can talk to me one-on-one, whatever works best for you.